Thank you for inviting me to talk about this interesting topic, endocrine disrupting chemicals. Tends to be in the news a lot, and I thought I would give a little different talk than you're probably used to, and it's much more of an introduction to what endocrine disrupting chemicals are, how they may impact human health, and how we're trying to study them here. And I've focused on phthalates and bisphenol A because that's my specific research area, but there's a wide variety of endocrine disrupting chemicals that are out in our environment. So first, in general, what are endocrine disrupting chemicals? So they're chemicals that mimic or antagonize normal hormones and can have permanent effects in progeny, as in organisms as well as in their progeny. And so what's interesting about that is that there can be a transgenerational effect. You can have an effect in offspring, and then you can have an effect in the next generation from a grandparent kind of exposure. So this was first brought to the forefront in the public by Rachel Carson with Silent Spring. And if those of you who remember, DDT basically was causing decreased reproductive capacity in a variety of birds. And a more modern day version of the story is called Our Stolen Future, and it's written by Theo Colburn, who is a biologist and also kind of philosopher. And this book really focuses on endocrine disrupting chemicals and how they may impact human health, and really brings to the fore how that effect can lead to effects in future generations. So that's kind of what's really, really novel about Our Stolen Future. And also, Al Gore has a foreword in this book, and I read this book in college, and it was one of the reasons that I went into this field. I was already interested in environmental science. That's what I had majored in college, but this was really what guided me towards wanting to work in human health as related to environmental factors. So types of endocrine disrupting chemicals. They can be natural or synthetic, and so I try to put natural first because people tend to think of these man-made chemicals, synthetic chemicals that we're being exposed to every day, but there are plenty of natural sources of endocrine disrupting chemicals, and there's certainly sources that are man-made that we choose to partake in. And so natural sources are like phytoestrogens, that's like soy-based products. Then there are fungal estrogens. Then there's synthetic EDCs like hormones, and so much of our population takes oral contraceptives. Certainly much of our female population takes oral contraceptives. There may be male contraceptives. I work in a male reproductive group, and I think there will be male contraceptives at some point, and they will be hormonally based. Then there are pesticides, industrial byproducts, there are plastic components, and then there are persistent organic pollutants. And so what's interesting here is that some of these chemicals can really persist in the environment over years, and some have very, very short half-lives. The newer chemicals that are being put on the market have much shorter half-lives because they're considered to be safer when they have a shorter half-life. But there are plenty of persistents that are still in our environment. And if any of you read the newspapers today or yesterday, there was an article on flame retardants in baby care products. And flame retardants are used very highly in California, and they're in a variety of baby care products. And they showed that over 80% of the products they tested had flame retardants in them that had probably been put onto the market many, many years ago, like decades ago. So effects of endocrine disrupting chemicals. What's interesting is that they can be estrogenic, anti-estrogenic, anti-androgenic, antithyroid, anti-progestinic, and some chemicals can have different effects at different time periods. So that's also a complexity of endocrine disrupting chemicals. It depends on when you're exposed and your sensitivity at that time period. So something like dioxin might be anti-estrogenic in the in utero fetal period, but then it may be anti-thyroidogenic at a different time point. It may even be pro-estrogenic at a different time point. And that makes it very, very difficult to study, certainly in epidemiologic human studies, but also in animal studies. And these are just some examples of endocrine disrupting chemicals on the right-hand side. So some of the toxicologic principles. When I was in undergrad, we tended to learn, and certainly when I was in pharmacokinetics and class in medical school, we learned that the dose makes the poison. So the higher the dose, the higher the effect. And what's interesting in endocrine disrupting chemical research is that there may be U-shaped curves. So it's a different kind of paradigm. It's not the dose makes the effect, it's the dose plus the timing makes the effect. So you could have a certain effect at a very low dose, And as you increase to a higher dose, you have a whole different range of effects. And actually in that middle period on that U-shaped curve, sometimes you don't see a lot of health impacts. So you have to know where you are on the curve. You certainly have to know the dose response in the biological organism that you're looking at. The timing of exposure, those are sensitive windows of vulnerability. I'm a pediatrician. I tend to focus on the prenatal period, the fetal period, and early childhood because that's a very, very sensitive window of vulnerability. But there certainly are other sensitive windows for organ development, neurologic development. And then half-life, I touched on this before, there's short versus persistent. I focus on chemicals that are very short half-lives, but they're very persistent chemicals in the environment, so they can have an effect in one generation, then have another effect in a different generation on top of the effect that they've already had. Then there's the concept of biological availability, and I think that this is often missed in research. When you think about something like lead, we know that lead is associated with definitive cognitive defects, especially when you're exposed prenatally and early in childhood. You have decreased IQ as you get older, depending on the amount of lead that you're exposed to. But when you look at lead in a biological system, it can be stored in the bone, and there it's biologically inert, and it's not out in the blood to affect the brain or other sensitive tissues. And so when people have kids who have very low blood lead concentrations, like something in 1 to 4 range, and they want to chelate, what they're probably doing is taking lead out of the bone and increasing its circulation in the body and actually making it more biologically available for potential harmful adverse effects. So thinking about the biological availability of the substance in the body is very important. And then toxicity. So one of the things I get asked a lot, and I just got asked this by a journalist the other day, is, well, if these chemicals are really harmful, wouldn't we know it? And the answer is no. And the answer is no for a variety of reasons. First, there are very few chemicals that are actually regulated that are put on the market. So we know pharmaceuticals are regulated, they're highly regulated. Pesticides are required to go under toxicity testing, and then food additives. But besides that, the chemicals that you're exposed to in personal care products or in your everyday common use, those chemicals are not required to necessarily go through a toxicity battery of testing. And even if they do, the industry is not allowed, or I'm sorry, does not release that information, does not want to release that information to the public. And so you really don't know what the toxicity is of a lot of these chemicals. And we have about 80,000 chemicals that are in regular commerce today, and of those, 5 have been regulated by the Toxic Substances and Control Act. And so it's just something to keep in mind that we have thousands of chemicals that are out there that we probably don't know the true toxicity of. And then genetics. Your genetic predisposition is going to really affect how the chemical affects you on an individual basis. And this is becoming more and more important as we move forward, but also adds to the complexity of research. So why are we so concerned about these chemicals? I get this all the time. Well, if the chemicals are in commerce, they're high production chemicals, wouldn't we know that they cause major health impacts? Wouldn't we see that in the population? Or we've been exposed for years and we haven't seen health impacts. Well, the traditional health outcomes that we've looked at, like infectious disease, they have been treated with antibiotics, and certainly our antibiotic research is robust within the pharmaceutical companies as well as within the university settings. But when you look at the current morbidities in the specifically pediatric population, I'll focus on, what we see is it's obesity, it's diabetes, it's neurodevelopmental disorders like ADHD and autism. Then there's reproductive disorders that you see a little in the little older kids, breast cancer, testicular cancer, and testicular malformations. And these disorders are not treated with antibiotics. These are chronic diseases that are really difficult to treat in the outpatient setting, and they're increasing rapidly. And a lot of people who work in environmental health and environmental epidemiology feel that there are both genetic and environmental factors that are contributing to all of these disease states. It's just much, much more difficult to study than a certain microorganism and how to kill that organism. And then we all feel like there's early programming of endocrine and metabolic processes. And this is not a new concept for those who work in endocrinology and human development, but it's kind of a new concept for researchers. So first I'll focus on phthalates. I like to call these everywhere chemicals. A lot of these chemicals are everywhere chemicals, but they truly are in our environment in a lot of different ways. So this was an article that we published on baby powder, shampoo, and lotion and how it was associated with increased phthalate exposures in infants. And I actually published this in a fellowship, and this was a quote from the article. "It's hard to trace where these chemicals are coming from. They could be causing harm, but we don't know to what extent." So you learn a lot as you move on in the research world, and what I learned is that quote says nothing. It doesn't really help when you're reading this kind of article. But it also reflects how difficult it is to talk about these chemicals in the lay press and talk about and communicate and translate the risks to the public. So we know that the chemicals are out there, but we don't know where they're coming from, and we know that they cause harm in animal studies, but we don't have a lot of human evidence. So what do we tell people in their everyday lives? And I'll get back to this at the end in terms of policy and what I say in the clinical setting. But it is difficult. Then on the right-hand side, it says sexy for her, and for baby, it could really be poison. And this is because a lot of fragrances contain phthalates. So in terms of consumer products, phthalates are in a wide variety of products. They're in flexible plastics in the upper left-hand corner. And one thing to keep in mind, especially for this audience, is that they're in a lot of medical tubing and medical equipment that we use every day. So likely a hospital-based population is having a much higher exposure on a daily basis than the general population. Then you have things like vinyl flooring, you have soft squeezy toys, then there's some personal care products in the bottom left-hand corner here, and phthalates are fragrance stabilizers, and they're also color stabilizers in these products. And then the food supply. So I've done versions of this talk over the years, and it's interesting what starts to come out. So before, all the things I just showed you were the sources of phthalates, and now we actually know that phthalates are in the food supply, and it likely may be the biggest source of exposure for a lot of the population. And so this is a really busy slide, but what I wanted to show you is that there's a variety of foods on the left-hand side, and you can see that there's a variety of phthalate compounds, and I'll discuss these more in a little bit. And you can see that there's very, very small concentrations of these phthalates in all of these foods. And by themselves, it's a very, very small concentration, but when they start to add up, then you have a much higher burden overall if you're eating foods every day that have some amount of contamination. And where is it coming from? It's likely not in the food product itself. It's likely coming from the processing over time. So my theory is that the farther away your food is produced, probably the more likely it is to be contaminated because it's gone through several processes before it gets to your plate. So it can be from conveyor belts, lids to glass jars, tubes. If you go into these factories where they make foods, they use large plastic tubing to kind of store something like a soup or any kind of food product. Then there's gloves. Gloves is likely a big source, plastic packaging, and then paper packaging as well. So what do we know about phthalates in our general population? Well, they're ubiquitous and there's widespread exposure. So there's 3 million tons produced and consumed globally, and then this is taken from NHANES. Are you familiar with NHANES in general? The National Health and Nutrition Examination Survey. So it's a study that they do, the CDC does, of the general population to look at a variety of health outcomes. And one of the things they do is look at body burden of chemicals. And so here on the left-hand side are some phthalate metabolites, and I will discuss those in just a second. So on the x-axis here are the different groups, so Mexican Americans, non-Hispanic blacks, non-Hispanic whites, children, and adults. And what's interesting, for some of these phthalates, you can see that children have a much higher exposure, specifically to MBP, MBZP, and MEHP. And these happen to be the more toxic phthalates. And I think that that's very interesting. And then non-Hispanic blacks have a much higher concentration of MEP. So in terms of phthalates, what are they? These are the parent compounds that we're exposed to in our products every day. And so this is literally what's put in the plastic product. So benzyl butyl phthalate, dibutyl phthalate, DEP, DEHP, and the ones that are in yellow are the more toxic parent compounds. So that's what we see in animal studies again and again that's causing a variety of health outcomes. The metabolites are actually what you're measuring in a biological matrix. So most of the time these are measured now in urine. And there's several metabolites for these parent compounds. And you can specifically see for DEHP, it actually gets conjugated in the body, and then some of those compounds then get transformed into oxidative products. So you can measure both those monoesters as well as those oxidative products. So how are phthalates measured in the body? We usually look at those metabolites, and there's a variety of biological fluids or matrices that you can use. Urine is the one that is used most for research studies. It's what is used by the CDC, but they have found phthalates in saliva, breast milk, semen, amniotic fluid, and blood. And I just put blood is not recommended to look at in blood because you may be seeing the parent compound before it's conjugated. Then they use something that you may know more about than I do, HPLC, ESI, mass spec. And so we are actually starting to do this here in the Environmental Health Laboratory, but it's very, very difficult to do this laboratory analysis. First, in terms of the samples, the collection of samples is really important. So if you're collecting samples in plastic, you may be introducing contamination into the sample, but then there's machine contamination. So just like I said before, like conveyor belts and food processing provide a lot of contamination of phthalates. The machines that we're using in our labs likely have phthalates in them because they have a lot of plastic components. So there's a lot of contamination to worry about when you start to undertake these kinds of laboratory analyses. So we're just starting to do these here. Historically, most people have used the Centers for Disease Control Laboratory to do urinary analyses, but given the amount of research studies that are going on, you can't use only one laboratory. So we've started to do it here in our Environmental Health Laboratory, and this is led by Russell Dills, who's the head chemist. And we began the process of setting up and validation in March. And I'll say that we're just starting sample analysis now, and that's kind of how long it's taken. And this is all they've been focusing on. And one of the reasons is it's really difficult to get rid of the contamination in the laboratory setting, and also to work on the limits of detection. And the limits of detection are very, very low for some of these, or the CDC standards are very low. So in terms of toxicokinetics, we talked about this a little bit, but routes of exposure, there can be parenteral, so that gets back to that flexible plastic tubing. So if you're hospitalized, you're likely getting a huge parenteral dose of DEHP. There's ingestion, there's dermal absorption, and then there's inhalation. And the toxicokinetics, or the metabolism, really depends on that route of exposure. So your parenteral exposure metabolism is different than an ingestion metabolism route. But overall, let's say you're ingesting phthalates, because most of us are, what we have is a rapid metabolism from a diester to a monoester, then to an oxidative product, and the half-lives are a few hours to days depending on which phthalate you're looking at. If it's a high molecular weight phthalate, it's a little bit longer of a half-life. If it's a low molecular weight phthalate, it's a short half-life. And then they're excreted primarily in the urine. So phthalates in childhood, this is one of the populations that we think is most vulnerable. It's premature infants in the neonatal setting. And so this group found urinary levels of DHP to be 50 times higher in preterm neonates as compared to those children from NHANES. So that's the data I just showed you. And when the FDA was reviewing phthalates, they released a statement saying that premature infants may be adversely affected by these chemicals. But I'll say that unless you're at a university-based setting, a lot of the NICUs that are out and they're not university-based really don't know that this FDA statement exists. And it's not a prescription to change all the equipment. It's just a statement that is out that's saying we should be considering that phthalates could cause harmful effects in these kids. So mechanisms of action. anyone who works in this area, we have to be a little humble because I think probably most of the mechanisms of action we don't know, but we do know a few. And one is that phthalates are definitely anti-androgens, and so they impair Leydig cell function in testicular development, which leads to reduced testosterone production. And it also leads to decreased INSL3 expression. And INSL3 is associated with testicular descent, which occurs in the third trimester of pregnancy. So a lot of these infants have reduced testosterone and reduced normal testicular descent. And this is kind of a good animal model that I like to show. So here, this is a pregnant mom who's exposed to a high dose of DHP, and you can look at the offspring, and this is days post-conception, and you can see that in the control, there's this nice testosterone peak that is supposed to occur. So this is pretty normal. The analogous process in humans is that at 3 to 4 months of age, we have something called a mini puberty, where we have a real big spike in infant hormones. And that's the analogous process that we look at in humans. But in animals, it's a little earlier. And you can see this nice testosterone spike in controls. And in the offspring of the mom who is exposed to DHP, you don't get that testosterone spike. And so that's some of the best biological animal mechanistic evidence that phthalates truly do decrease androgen exposure in utero. And from that kind of data and many hundreds of animal studies, we have something called the phthalate syndrome. And here you can see a pregnant dam again who's exposed to DHP, and what you see are a variety of malformations in the offspring. And this is to the epididymis, the vas deferens, seminal vesicles, prostate. You see hypospadias, undescended testes, and you see nipple retention. And they told me that most of you are medically oriented, so I'm not going to explain these. Are most of you MDs or in healthcare in general, so you understand? Okay. I talk to a lot of different audiences, so sometimes I need to explain what hypospadias is. And the one thing that's very, very important here that we look at in our own studies is anogenital distance. So with all of these malformations, you get something called a reduced anogenital distance, and that's truly the distance between the anus to the genitals. And that's a reproductive toxicity endpoint in a lot of Environmental Protection Agency studies, studies where they're truly testing toxicity of chemicals. And when there's a reduced anogenital distance, you usually see this variety of malformations. And so that's something that we start to look at in humans, and I'll get into that in just a second. So what do we know about humans? Those are the animal studies, the phthalate syndrome and reduced anogenital distance. What has been put forth in terms of hypotheses is something called the testicular dysgenesis syndrome, and this is from Neil Skekibak and his group in Europe. And what it postulates is that there are environmental factors and genetic defects that will lead to testicular dysgenesis, and this is testicular dysgenesis in utero. And that leads to disturbed Sertoli cell function, Leydig cell function, which then can lead to impaired germ cell differentiation, androgen insufficiency, and you will get hypospadias and cryptorchidism. And as these animals grow, this happens in animal studies, but this is what's postulated in humans. You see reduced semen quality and then carcinoma in situ and testicular cancer. So in the animal models, they see hypospadias, cryptorchidism, they do see reduced fertility, they see testicular tumors, but not true testicular cancer. It's hard to create an animal model of testicular cancer, so what they're seeing right now is just tumors. But this is what's been put forth for humans, that maybe there are these factors that are leading to testicular changes very early on that lead to later life effects. So it's that early programming of disease. It's very early on that the testes are programmed to have normal semen production in the future. So there is an increased incidence of testicular dysgenesis syndrome in males in the United States and other Nordic countries. So this is part of why are we so concerned. Hypospadias has been increasing in the U.S. population over the past several decades. And on the left-hand side, I apologize for the quality of this slide, this is rates of testicular cancer in European countries. And you can see that concurrently, there's been a big rise in testicular cancer, which is a disease of younger males, adolescent into their 20s and 30s. And we see these rises, but we have no idea what's actually causing them. And people who work in this field truly believe that there are environmental factors that are impacting this incidence rate. And then in adult males, we do see some human evidence of altered sperm quality. So this is a little slide to say the bad news is that 99% of you will fail, and this is fertilization class. And unfortunately, maybe more will fail with some of these environmental factors that we're introducing. So on the right-hand side, these are graphs that are showing the odds for being below a reference sperm concentration and sperm motility as by WHO standards. And then on the x-axis, these are quartiles of phthalate exposure. So the quartile 4 is the highest quartile, quartile 1 is the lowest quartile. And this is monobutyl phthalate. And so you can see that with increasing quartiles of exposure, you have an increased odds of having reduced sperm or having sperm concentration below the reference, the WHO reference range. And here you can see with increasing quartile, you have odds of sperm having decreased motility, and increased odds of sperm having decreased motility. And so this has actually been replicated in several adult studies. And so this is with concurrent phthalate exposure. This is not early. It's if you're exposed at the same time that your sperm quality is decreased if you have a high exposure concentration. Then what do we know about childhood populations? Well, Katarina Main and her group found a significant association between breastfeeding, phthalate exposure, so what that really means is breast milk phthalate exposures, and changes in luteinizing hormone and free testosterone concentrations in newborn boys with cryptorchidism. So this was some of the first human evidence to show that really phthalates are associated with changes in hormone concentrations in humans. And then Shauna Swan, who's someone that I work with very closely, found a significant association between prenatal phthalate concentrations and that decreased anogenital distance and reduced testicular descent and decreased penile width in infants. And so this was one of the more definitive studies actually really showing that phthalate exposure in the prenatal period is associated with changes in postnatal life. Now I should say that this decreased anogenital distance and reduced testicular descent and decreased penile width, these are not, in these infants, were not concerning enough to prompt medical attention. It's just compared to the infants whose mothers were not as exposed at high concentrations, they had a decreased anogenital distance and reduced testicular descent. So you have to think about it on a population level. So these are some of the phenotypes that we look at in our studies, the anogenital distance and the anoscrotal distance, and then penile width on the right-hand side. And I like to just show this slide to show you that this is truly what we're doing on a daily basis, and we're trying to relate these to other health outcomes. And because it's so difficult in human epidemiology to study some of the more rare outcomes like hypospadias and cryptorchidism, you would have to study thousands of women during pregnancy and then their offspring. So what is the significance of these intermediate phenotypes? Well, in animal studies, I said that they're reproductive toxicity endpoints and the well-known markers of in utero androgen exposure. Then there's one human study that documents an association between these markers and male reproductive abnormalities. So that's saying that kids that do have cryptorchidism and hypospadias do have a decreased anogenital distance. And it may translate to humans and therefore may be sentinel markers of future male reproductive outcomes. And this is just some other research that focuses on some of the other outcomes associated with phthalates. DHP metabolites have been associated with changes in thyroid hormone and total T3 levels in adult men. And then more recently, they've been looking at phthalate exposures as related to neurodevelopmental outcomes. And there was a cross-sectional study that showed that phthalates were associated with changes in omission and commission errors in these continuous performance tests that they do in behavioral studies. And the last study down here showed that phthalate exposure in the third trimester was associated with changes in social cognition and social communication. And that's interesting because when you think of what actually leads to sexual dimorphism in the in utero period, so what leads to male play and female play, it's your hormone concentrations. And so one of the things that the behaviorists are starting to look at is changes in behavioral play in children who have been exposed to these chemicals. So that just brings me to the end of the phthalate portion. This is a study that we're doing right now. It's called the Infant Development and Environment Study. The PI is Shauna Swan, and she is now at Mount Sinai, and I'm the site PI and clinical director here, and we have a number of co-investigators, urologists and OBGYNs and other pediatricians. And what we're trying to do here is test the hypothesis that that prenatal phthalate exposure is truly associated with reproductive outcomes in male infants. And so we're recruiting 800 women overall at 4 different centers. Here we're recruiting 200. And we're looking at these anogenital outcomes in their infants. And so the idea is to see if these shortened anogenital distances or these smaller testicular volumes are truly associated with a higher phthalate exposure in the prenatal period. And Ellen Lashansky's here, and she's one of our study coordinators at the U and is responsible for recruiting our first 80 women or so, hopefully the full 200. So now I'm going to switch gears to Bisphenol A. So Bisphenol A is a chemical that has been in the news much more recently, and there are articles coming out left and right about Bisphenol A. And so what is it? It's a chemical that is used in hard polycarbonate plastics, and so that's the Nalgene bottles and the baby bottles down bottom and the water coolers. And it's also in dental sealants, and it's in cans, and it's in actually the can lining of these kinds of metal food cans that we use. And the reason it's there is because it protects the can from being degraded by the actual food product. And so the more acidic the food product, the higher the likelihood that there will be a high BPA concentration in your can lining. So something like canned tomatoes likely has very high BPA concentrations. Something that's more pH neutral will have higher BPA concentrations. And I should say that most US manufacturers have taken Bisphenol A out of baby bottles and out of the Nalgene bottles as well. So again, this is ubiquitous and widespread. It's a high volume production chemical. 8 billion pounds are produced per year. And again, this is taken from the NHANES survey, and you can see the BPA concentrations, the geometric means, and the percentiles. These numbers look very small, but when you actually look at the animal studies, you see effects at these concentrations, at the concentrations that we're exposed to in the general population. So how is bisphenol A measured in the body? Well, there's free and conjugated form. And so the free form is actually what's more biologically active and is what is estrogenic. And then there's the conjugated form. And so it goes through first pass metabolism through the liver. And they used to say that it would go through first pass, 80% to 90% would go through first pass metabolism definitively, but actually what we're seeing now is it's much, much lower. There's a lot of the free compound that circulates in the body when you're exposed. And they found bisphenol A in a variety of biological matrices. Urine, again, is what we use in the research studies, what's most widely used, but it's been found in saliva, breast milk, semen, amniotic fluid, placenta, adipose tissue, ovarian follicular fluids that they've taken from IVF pregnancies, and then also in blood. And here for bisphenol A, they usually use solid phase extraction coupled with online HPLC and tandem mass spec. And we are also doing this in the EHL laboratory. We're not using the exact same methodology that the CDC uses. We're using a direct injection methodology. But I think we're going to get the same kind of sensitivity or very similar. And contamination, we talked about contamination with the phthalates. For bisphenol A, it's even worse for some reason, and I'm not exactly sure why, but it has taken a very long time for the lab to decrease the contamination to the point of where you get true limits of detection in the 1 to 2 part per billion range. So mechanisms of action. So bisphenol A is a weak estrogen, and it's also an anti-androgen depending on when you're exposed. It's rapidly metabolized within 4 to 6 hours. So I should say bisphenol A was actually created at the same time DES was created, which is diethylstilbestrol, which is a very, very potent estrogen. And it was too weak to be used as a pharmaceutical, so they didn't use it anymore. And then it was an industrial plastics manufacturer that found that it really worked well in a plastic matrix. So we do know that bisphenol A is truly an estrogen, was created for that purpose, and now it's being used for a different purpose. It binds to estrogen receptors, ER alpha and ER beta. It can stimulate rapid cellular responses at very low concentrations, and it upregulates estrogen receptors. One of the other things it does is that it binds to alpha-fetoprotein, which usually binds estrogen in the body, and that leads to increased estrogen circulation when you have this protein that's actually getting bound to the chemical instead of to the biological endogenous estrogen. So in terms of summary of findings, there's not as robust a database of bisphenol A studies in humans as there is with phthalates. It's something that's being studied right now, and it's actually being studied by one of our graduate students who's here, Kristen, who's looking at bisphenol A and endometriosis in a study. But what we do know from the animal studies is that bisphenol A exposure can lead to a variety of health outcomes. There's male reproductive tract defects, not to the extent that we see with phthalates, but certainly still a variety of male reproductive tract malformations, neurocognitive disorders, diminished differences in sexually dimorphic behavior, early puberty, increased body size, and then at low doses you see breast, uterine, prostate tumor cell proliferation. And the reason these are all in yellow is because these are the low dose studies. So one of the arguments that people make about toxicity studies or human epidemiology, environmental epidemiology in general is, well, the animal studies are dosing these animals at very, very high concentrations, and humans would never, ever be exposed at that high of a concentration. But what is really interesting about bisphenol A is that at very low concentrations, you see a variety of health impacts that are different than those in white that you see at high dose concentrations. And the low dose health impacts are actually a little more concerning to me here, the breast and uterine prostate tumor cell proliferations. Those are all cancers that have been on the rise for many years now, and we don't know exactly why. So in terms of human epidemiologic studies, there are correlations between BPA and serum sex steroid hormones in adults. There are weak associations between bisphenol A exposure and delayed onset of breast development in girls. I think that those human epi studies are very weak at this point, so I would never say that bisphenol A was associated with early development of breast tissue. And then there's been a study that looked at prenatal BPA exposure and increased hyperactivity and aggression in 2-year-old female children. So one of the studies I do like to cite is, this is an animal study, but I think it's really interesting. So they dosed pregnant mice here at 25 nanograms per kilogram from day 9 of pregnancy through birth. So that's a really small concentration, 25 nanograms per kilogram. It's certainly something, a concentration that humans would be exposed to, if not higher. And then they examined the mammary glands of the offspring at day 30. And so on the left-hand side, you see here a control animal, and this is normal gland development. You see normal mammary ducts, normal terminal buds, and here on the exposed offspring animal, you see increased terminal bud growth and density, a decreased number of apoptotic cells, and basically disordered cell proliferation if you start to look at some of the other slides. And so this is really interesting. A lot of the animal researchers truly feel like this is the precursor to carcinoma in situ. And so they're inducing, with a very, very low dose of bisphenol A exposure in the prenatal period, major changes in mammary tissue. So this was taken from the study, the perinatal exposure to bisphenol A alters peripubertal mammary gland development in mice. And then there was another study of effects of BPA on breast cancer and its risk factors that found that the median serum BPA concentration was higher among cases of breast cancer compared to controls. But there were a variety of weaknesses in a study like that. The other big finding about bisphenol A and what was in the news a couple of years ago was how bisphenol A was associated with a variety of cardiovascular outcomes. And this was actually published in JAMA. And here you can see the mean BPA concentration, and you see a variety of health conditions. And you can see that the mean BPA concentration is much higher in these conditions. And basically, this study was published in JAMA because they found very, very high odds ratios that you would not expect to find due to chance alone. So there were increased odds of having these conditions in people who have very high BPA concentrations as compared to those who didn't. And those confidence intervals, if you look at the paper, are narrow and they're specific, and this was a very, very large population. And so this was very concerning. And then the other thing I like to touch on with bisphenol A is related to obesity. So in endocrine disruptor research, we start to talk about something called obesogens, and not only endocrine disruptor researchers, but lots of obesity researchers are starting to talk about how there are certain substances or certain environmental factors that may lead to different metabolic set points, and they may promote adipogenesis. And so this is specifically has been seen with DES. So that was a synthetic estrogen that was used to prevent miscarriages many decades ago. And what they saw was that exposure, when you exposed animals in utero, the offspring were obese. And then they continued to be obese even if you restricted caloric intake and increased exercise. And then when they bred those mice, the third generation was also obese, and they had increases in leptin and adiponectin, and we know that obese kids, obese adults, have increased levels of leptin. So that was really interesting. It's a transgenerational effect with a hormonal agent. And in pediatrics, in general pediatrics, we see this again and again. You'll see a family where the parents are not obese, they have 3 kids that are completely normal, then they'll have one child who truly has a different metabolic set point. They're eating the same foods, they're on a restricted caloric intake, and they do not lose weight. There's really something about their metabolism that was programmed at a very early age that's very difficult to overcome once you get older. And I think it's one of the unfortunate parts about obesity. It's truly in the public seen as, well, if you increase your exercise and decrease diet, you will lose weight, and that's not necessarily the case. If you increase your exercise and have a better diet, you will be healthier, but that does not mean that you're necessarily going to lose weight. And that's very sad, especially the kids who are obese and they start in toddlerhood and they just continue on. And then the other population in the pediatric setting is adolescents, where you'll see a lot of kids who have a normal weight gain, normal height velocity, and then they get to puberty, and something changes and they gain 70 or 80 pounds in a year. Much, much more weight than the average person could gain in a year. And they continue to gain that weight, and they have a lot of trouble keeping it off. And so that's another set point that I think is really important, is right at that pubertal time point. So these are some of the studies that I won't get into them in detail because they're more basic science studies that look at the estrogenic effect of bisphenol A on pancreatic beta cell function and inducing insulin resistance. But I think that this is where bisphenol A research is going to go, our endocrine disruptor research is going to go in the future. So now I'm going to switch gears and talk a little bit about how we avoid these chemicals. So I work in something called the Pediatric Environmental Health Specialty Unit, and we do environmental health consults, and we do them for families and governments and healthcare providers. And this is what people want to know about. Well, how do we avoid these chemicals? So the first thing that I'll tell people is that when you look at plastics that you're using, if they're made in Europe or they're made in the United States, they'll have a recycling code on the bottom, and it has numbers in that recycling code. So plastic number 3 tends to contain phthalates, and plastic number 7 tends to contain bisphenol A. Not always, but these are the plastics that we know do contain phthalates and bisphenol A. And so for those specific plastics, you can either avoid using them at all, or you can try to use them in a little safer way. So don't microwave your food in plastic, don't put hot liquids in the plastic containers, don't dishwash them because that leads to degradation, and then use alternatives to plastic packaging when possible. And you can use glass or a different kind of plastic, like a polyethylene plastic. What I truly tell people is to try to choose alternatives to processed food, to eat fresh fruits and vegetables. And that gets at this next slide. So in general, how to cancel families, and I'm not sure in terms of your laboratory analyses if you do environmental contaminants like metals or endocrine disrupting chemicals, you may as the years go on. And people always want to know a certain concentration. They want to know, well, what is my body burden of this? What is my phthalate level? And one of the things that I always tell people is that doesn't mean anything. Even if we get that number, it's not correlated with a health outcome. So I try to get people away from that concept and move towards prevention, and recognizing that there's limited data on health impacts of modern chemicals. One of the things that we struggle with, especially in the Seattle region, is that there are a lot of families that will go to alternative care providers. And alternative care providers will tend to do a lot of environmental testing and have a lot of difficulty translating that testing to human health impacts. And so instead, I try to just focus back on, we just don't have good data on what the health impacts are of these chemicals, so let's not try to go that testing route. Let's work on prevention, because that's the most important part anyway, and you'll get there whether you do the testing or not. You're still going to focus on prevention. In terms of decreasing exposures as much as possible, you could never get to zero. Places where I refer people are the Environmental Working Group website, which talks about pesticides in foods, the Environmental Defense Fund, which looks at safe seafoods and talks about mercury, the American Lung Association, which tells you how to keep your indoor environment clean, and then educating with appropriate resources. In terms of policy implications, so what is our country or other countries doing about this if there are harmful human health impacts, and there are more and more studies coming out? Well, the European Union has by far been the most progressive. They banned the use of these chemicals in 2005, some of the phthalates, I should say, in children's toys and childcare articles. I personally think that banning in specific products is probably not going to help that much, because they're ubiquitous and they're likely in the food supply. But certainly it's not going to hurt to ban in products that specifically children are exposed to. In 2007, in Washington State, we passed the Children's Safe Products Act, which restricted phthalates in children's toys. That was preempted by some federal legislation in 2008, which was the Toxic Toys Bill, which restricts phthalates in children's toys. This is just an Endocrine Society statement that I like to put up. It says that scientific societies, such as the Endocrine Society, should partner with other organizations with the scientific and medical expertise to evaluate the effects of endocrine disrupting chemicals in humans. And one of the points that I think is really important with environmental health research is that it's incredibly multidisciplinary. You have to have the people who understand the environmental exposures, you have to have the people who understand the metabolic processes, the people who understand the health impacts, and then the people who can relate it to policy and translate it out to the public. And so it really requires collaboration across a variety of disciplines, and I'm really happy to see that the endocrinologists are moving forward in this area. So this is just the unit that I work in, which is the Pediatric Environmental Health Specialty Unit, and it serves, I think I just said, healthcare providers, public health professionals, communities, families. We try to do much more provider-to-provider education, so it's kind of the train-the-trainer model, so that they can educate their future patients and try not to focus on individual families. But it's funded through the EPA and ETSDR. And we do consultation for the Region 10 area, which is Oregon, Idaho, Alaska, and Washington State. And you're welcome to call us at any time, and we're happy to answer any questions that you might have. And I just wanted to acknowledge Shauna Swan, who's been very involved in my research over the years, and the entire TIDE study team. And with that, I'm happy to take questions.
Does microwaving with plastics extract, or any sort of heating, extract more of these chemicals out of plastics than simply just storing it overnight in a fridge or at room temperature?
Yeah, it does. So the heating process will increase the leaching of the chemicals from the phthalate matrix. They're not bound very strongly, basically, in the matrix. And so the more you heat, the more leaching you're going to get.
And the recommendations on not to do these things with these plastics were for the number 3 and 7, yeah, and not for the other ones?
Not for the other ones. The other ones, when you look at how they're created, they don't have these chemicals in them. And so they won't be leading to phthalate and specifically bisphenol A exposure. That doesn't mean that there aren't other chemicals, but those chemicals are not known endocrine disrupting chemicals.
So there's plenty of targets for this sort of research beyond phthalates and BPA, and I'm wondering if there's any kind of agreement in the sort of scientific organizations that care about these things, about what would constitute a convincing study for any one of them. I mean, is there a conscious postulates of endocrine disruptors or of environmental toxins or something like that, such that if the result came out as X, people would be universally convinced that a given substance was a problem?
Yeah, I mean, that's a really hard question, and I think that that's not just related to endocrine disrupting chemicals, that's related to all research. How many studies do you need to say that we know that this chemical causes this effect? I will say that Shauna Swan's work, where they did look at that prenatal phthalate exposure and the male reproductive outcomes, it really, really corresponds to what we see in the animal literature. So overall, I think that those studies that can really replicate what is seen in hundreds of animal studies are the studies that are trusted the most, just because we know the biological mechanisms and we're seeing the same mechanisms in humans. I don't think that there are postulates, not that I have seen yet. I mean, if it depends on who you'd ask, because there's some people who say, well, if you have increased cell receptor uptake or increased gene expression, then that's enough. And then there's some people that say, unless you have a hard health outcome that's adversely impacting the population, then you can't say much.
What's been the response of the chemical industry? Are there other plasticizers that people are trying to replace these with?
Yeah, there was actually just an editorial in the New York Times last week about that, and for bisphenol A specifically, they have, before, when they were replacing bisphenol A, they replaced it with something that was biologically inert, or what we think is biologically inert. Now they're starting to replace it with another substance that may be estrogenic as well. So I think that the response is that they would like to get these chemicals out of their products, but it's difficult to do that. So the manufacturers of like the plastic bottles, they can do that. But the manufacturers of some of these other products where it's coming in through contamination have a very difficult time doing that. For the Washington state legislation, I sat on the governor's panel to implement that act, and one of the things that I heard again and again from the small retailers and from the companies was that we don't know where it's coming from, which to me, as a scientist, I'm like, of course you know where it's coming from. Like, you can trace that, you can find out. But when they started to talk about it more and more, it's like 1,000 different factories that are creating different substances for one small children's toy. And they truly have a hard time tracing back to what's being put into those original substances. Overall, they'll say, if you go to all of their web pages, they'll say that there's no evidence to show that there are harmful health effects at the concentrations that they're being exposed to. And in an individual product, I might agree with that, but the problem is that we're exposed to we have a cumulative exposure over time.